All right, class. This is a quick set of examples from Lecture 3, just some supplementary material. So just to remind you, Lecture 3 was a review of Math and Python. So I'm going to put that down here. Math and Python review. And this was day 2. Okay, and I just wanted to add a couple things to the lecture supplementary material. So this will be just a supplement. Okay, so we had talked about A, we did derivatives, and B, we talked about integrals. Okay, and we did double and triple integrals. And I just wanted to to do a quick integral example in case anyone needed that. So the idea here is to calculate the integral of this function, f of r theta is equal to r cosine theta, over a quarter circle. With radius 2. Okay, so define this integral A, is what I'm going to call it, and I'm going to do a double integral. So let's draw our area over here real quick. So I have, my quarter circle. Oop, not the best drawer on this, but it is what it is. Okay, so I'm going to call that radius equal to 2. Okay, and then I'm going to go from 0 here, okay, up to an angle here. This will be my theta, okay, of pi over 2. Okay, so that means I'm going to put f of r theta here. I'm going to do the integral of f of r theta, and then remember I need r dr d theta because this is polar coordinates. Okay, so okay, and then I need my limits here. So r is my inside one, so I'm going to do 0 to 2. Okay, and d theta is the outside integral, so that's going to be 0 to pi halves. Okay, so now I'm going to do my integral. So I need to write down what the function was. 0 to pi halves and 0 to 2. Let me try and adjust this. And then I said it was r cosine theta, r dr d theta. Okay, so the first thing I do this first integral on the inside. So notice r, that gives me an r squared. Okay, cosine theta doesn't depend on that, so I'm really doing the integral of r squared cosine theta. So r squared is going to become, and the antiderivative is r cubed over 3. So that will now become 0 to pi halves. And I'm going to put this in a bracket. I'm going to have r cubed over 3 cosine of theta. And I need to evaluate r at 2 and r at 0. And then this will still be inside d theta. Okay? So I can go ahead and evaluate that now. So if I do that on the next line, I evaluate r at 2, that's 2 cubed is 8, so that's 8 thirds and then 0. So I'm going to have 8 thirds minus 0 of cosine theta, still my integral here, 0 pi halves d theta. Okay, and then the 8 thirds is going to come out, and now I just have to integrate cosine theta d theta. Well, the integral of cosine of theta should be sine of theta, right? So I should have sine of theta. I need my 8 thirds in front. and I'm going to evaluate that one from pi halves to 0. Okay, the sine of pi halves is 1, and the sine of 0 is 0, so this is just going to be 8/3 of 1 minus 0, which is 8/3. Okay, so there was kind of a simple example doing double integral. Okay, I wanted finally to give one more little supplementary thing just to add on to our lecture in case you wanted to know. And these are some identities. Okay, and these are just to refresh your memory. So that's all this is for, just to refresh memory. Okay, because we'll see these later. Okay, so here are some derivative identities. Okay, and let me add a new page here, new page after. Okay, so the first one is if I take the curl of a gradient of a function, that's 0. Okay, so curl of a gradient is 0. Okay, I can also take the divergence of a curl, and that is also 0. So if I have some vector A and I take the curl of it and I take the divergence, that's also 0. Okay, so this is divergence of a curl. Oops, it's kind of ugly. Curl. Okay, and then last but not least here, if I take the divergence of a gradient, okay, that is something we call the Laplacian, which we write as del squared. Okay, notice that this here is vector dotted with a vector. This is a scalar. Okay, so this is the Laplacian. Okay, one more quick thing to mention about these derivative identities. Because these are 0, it turns out that any vector function, f, I can write as the sum of two parts. A part that is a gradient and a part that has a curl. Okay, and this is called the Helmholtz decomposition. Helmholtz decomposition. Okay, so it turns out that any vector field can be written this way, and so this part here, okay, this is a curl-free part. Okay, so there, this can't have any curl because of this guy. Okay, and this one, okay, is divergence free. Okay, so if I take the divergence of that, that gives me 0. Okay, so do I have that right, or do I have those backwards? I think I have them right. Okay, so anyway, the basic idea is that I can write down a Helmholtz decomposition, and I have a curl-free and a divergence-free part. Okay, so if I had something like this, I would end up with what we call an rotational flow, and I could write something like this if I have what we call an incompressible flow. Okay, so that's enough for the derivative identities. The integral identities. Okay, I'm just going to write these down. So if I have one here, if I have an integral over a surface of some scalar function f, okay, that is equal to the volume integral over the gradient of f. Oops, I forgot. This has to have a volume. This one over here has to have d surface. Okay, so this would be like a 2D integral and a 3D integral. I just wrote them as a single integral with a v for volume. Okay, and n here is the outward normal from some surface. So if I had a surface, I could have some outward normal vector. Okay, so that's for a scalar function. That one's a little uncommon, and I'm not sure if we're going to see it, but for completeness I included it. The most common one that I'm sure you saw in your calculus class is if I have, instead of f here, I have this vector a, ds, and it looks very similar, okay? And this is del dot a dv, okay? This is called the Gauss divergence theorem. Okay, lots of hooks on them. Okay, and the Gauss divergence theorem basically says if I've got some surface, okay, with my outward normal here, okay, it says that if I add up all of the a coming out of that surface, so if I have a, okay, some function a, I'm going to add all of it up, n dot a, so I'm going to find out how much is coming out, and I add up all of its surface, okay, that has to equal the volume integral of the divergence of a coming out. Okay, so you can sort of think it like the divergence of a is kind of like how much is coming out of a little point. Okay, and you add all that up within that volume, okay, the divergence of a, and that has to equal that. All right, and this is really a conservation law. Okay, this is conservation law. Okay, and we're going to use that later in the class to talk about the conservation of momentum. Okay, finally, you can also write this for a tensor. So again, this one is not as common. Maybe I should just do Gauss divergence theorem. But here it is for completeness sake. So I can rewrite this as del dot tau dv. Okay, so I can have a scalar, a vector, or a tensor, and all of those. Okay, that was a little supplement I wanted to add. Thank you much.